When I was getting dressed today, I was like, hey, I better look good for my nerd presentation. So I was like, should I wear the robot t-shirt or the anime t-shirt? So yeah, I went with robot t-shirt and jeans. So, who says that geeks don't have a sense of style? So I just want to say, seriously, thank you all for coming. It's awesome to see so many people interested in, what does ML stand for? Machine learning? Something like that. Machine learning and artificial intelligence. I think that I was really taken aback by how many people RSVP'd. It was very exciting and also like just a little bit stressful because I was like, oh, where am I going to do it? What's going to happen? What are they all going to want? Are they going to have a good time? So I I was talking to my friend about this. And I was like, oh, I'm all worried about the machine learning meetup. What are we going to do? And she said, hey, why don't you have it at a bar? That way, if people get bored of your talk, they can just get a beer. So I said, hey, that's a good idea. So strategic venue choice. Now, I really want to talk to everyone. That might not be possible today, but I will definitely talk to as many people as I can. I want to know, are you a practitioner? Are you academic? Are you commercial? What color underpants do you wear? Do you like beer or spirits? Like one of the important questions. So yeah, I'll try and get around, and if you see me and want to talk to me about something, just like grab me. I'm here for you, man. Yeah, and so the format is that I'm going to talk until the next thing starts, which is at 7:30, and then we're going to hang out, and we can all meet each other and see who else is interested in ML. And that's the bit I'm looking forward to as well, because this talking bit, So yeah, definitely stick around after the talk. So. When I was doing this, the way I normally do talks is I kind of saunter up and just talk about some crap. And that works for like the 10 people meetups because we're just eating pizza and drinking beer anyway. But when all these people are speaking, I was like, ah, shit, I'm going to do a talk that's good. So I went to Google, and like you pray to Google, like the great God Google. You're like, Google, how do I make a talk good? Because will I have a good harvest? And so I was, and then apparently you meant to start off with a joke. So here goes. Here's my joke. There is this panel. I think they're like a Senate committee or something. I don't know how Americans work. And they're investigating the efficacy of the Star Wars project. And so this engineer gets up and he's being grilled by the Senate. And they go, well, what have you accomplished so far? And he goes, we've got an accuracy in 1 part in 2 to the 10, and we need an accuracy of 1 part in 2 to the 20. And, the senator looks happy and he says, oh, great, so we're halfway there. That's a nerd joke. But that's funny for 2 reasons. One, because the senator is bad at maths. And the second reason it's funny is because back in, I think, 2012, I was reading this paper by Google where they had done 1 billion parameter neural networks. So that's 1 billion connections in the neural network. And I was looking at that and I was like, okay, so this model has like 10 to the 9 connections, and the brain has, say, 10 to the 14 synapses. Ah, so we're halfway there. So there you go, there's your joke. Oh, hang on a minute. This meetup is about community, mastery, beer, and any other beverage of your choice. We want to do things, work on cool problems together. That slide should have come first. I literally put these together hours before I needed to speak. That's a new record for me. So the title of this talk is Principles of Flight. And I think that there are a lot of really good analogies between the guys that did this stuff. I think they're called the Wright brothers or something, I don't know. And AI. I think that back when we were sort of experimenting with heavier than air flight, there were a lot of different opinions. Like, one, we can't do it, it'll never work, it's too hard. And also there was a lot of academics working on a lot of money and a lot of commercial interest in making flight work because they were like, well, it'll change everything. So pretty much everything is the same today. We've got lots of people working on AI at Google, Facebook. They're all plowing hundreds of millions of dollars into it. And everyone is trying to find that magic formula, that thing that actually flies, that thing that actually thinks. And, there's some success and there's some failures. And I think that what's really interesting about that analogy, though, is that the Wright brothers weren't really academics and they weren't really that big. They just, you know, they were interested and they gave it a crack. So I think that it's just as likely that, you know, one of you guys, definitely not me, but one of you guys will crack the thinking thing, and it's just as likely it's you as opposed to Google. Because what a lot of people don't tell about this story with the Wright brothers thing is that there was like a very large commercial team working on it at the same time, and they were failing, essentially because they had more money, but they didn't have more better, which is what they needed. So, yeah, buy more better. So I was at Pause Fest this weekend, and it was not terribly good, but there were some sessions from the people, the producers of This American Life, and I love This American Life, and I hadn't actually written my talk yet. So they were talking about how to make something compelling, how to make your content compelling. I said, oh, yes, please. So they said you have to have good characters. I said, oh, fuck, okay, characters. So here are my characters. We've got the Wright brothers, and I already introduced them. We've got the juggling, unicycling professor, and if you're in the know, you'll know who that is. We've got the silly Nazi-fighting genius, and these characters are meant to be lovable as well, so that guy is definitely lovable. This guy, yeah, come on, Nazi-fighting, what's not to love about that? And we've got 300,000 floating point parameters. Less lovable than the other ones, but you know, you'll warm up to it. And we've got a dictionary. And I think you'll also warm up to the dictionary, it's a special dictionary. So they said that once you got characters, you need stakes. You need something to be at stake. And like, there was some consternation on what I should put in stakes. It's like, oh, AI will change the world. We'll all be riding flying ponies that were invented by AI, super smart and better than us in every way. Yeah, maybe not, but I think that, like, again, with the Wright brothers analogy, the plane did really change the way we think about, you know, our world and our society. And, you know, if we have things that are like us, but not, that will be great. If I think someone once said the best way to predict the future is to invent it. So I also think that like, the best way to meet aliens is to build them. So get on that. Okay, so yeah, there'll be a million ways we can't live without it. It's one of those things like the mobile phone or the plane and like the internet. It's kind of like no one knows how you'll use it until everyone does. You're like, well, fuck, what will we do without it? So I think that's kind of what will happen with AI, that at some point you'll have AIs who'll be like, book me an amazing trip to Paris. And they'll be like, okay, yes, sir. Your wish is my command. And then you'll have an amazing flight in Paris. You'll be like, gee, isn't AI great? But also, a wet brain is a terrible thing to waste. So, like, sometimes I think about some of my friends who, as far as I can tell, their job is like being a human database. It's like they answer like calls or they get emails, and then they look something up, literally in a database in front of them. And it's like they're like a terrible front end to the database that's really expensive. And it's like, we could fix that. Like, we really need to fix that because it's the waste of a person's life. I don't tell them that, but I think... okay, once I did. So we really want to avoid those situations, and we don't need people doing those jobs, and there's no reason why AI couldn't. Yes, we move on to our juggling, unicycling professor. I'm just going to check the time so we don't run over. Okay, now we're playing back. So, the juggling, unicycling professor is, of course, the one and only Claude Shannon. He invented this thing called information theory. And at this point, you're like, why the fuck do I give a shit about information theory? I came here for ML and AI. But, you know, bear with me, all will be revealed. So, Claude Shannon, the slide, invented a thing called information theory. He also invented a whole bunch of new juggling patterns. He was really into unicycling. I think you could unicycle and juggle at the same time, but, you know, so, I put it out there to the crowd. He also invented this thing called the ultimate machine, which sat at his desk. And, you know, it may be an apocryphal story, but apparently this machine was pretty powerful. You know, and if anyone could solve the problem of, you know, machine intelligence way before anyone else, it was Claude Shannon. So I went through the internet and managed to find a video of this machine in operation. So here we go. Okay, let's do this. He's turning it on. Okay, there you go. Man, that's the machine working. Yeah, if we ever design AIs, we'll need to think of objective functions, which isn't like quit early. This life thing you humans do too complicated. Okay, so here we go. Here are two flashing dots. I know, fucking riveting. Okay, now here there are 2 bits of entropy. Why are there 2 bits of entropy? Because there's two things, and they can be on or off. And they're just totally unrelated. There's on, they're just off, they're just on, they're off. Yeah, you can watch them forever. That's JavaScript. but here's another system. Now this system only has 1 bit of entropy. And you can tell because even though there's 2 lights, there's 2 measurable things, they're on or off together. So you could kind of describe the entire system state with 1 bit. And that's really important because in the end, what we're trying to do with like machine learning is to find those systems and say that's 1 bit, that's really 1 bit. That behind the scenes there is something controlling everything, and or there are less bits to describe the system than are kind of on the surface apparent, and that's very important. And this is the reason why I chose the Principles of Flight title, because when you think about it, even though a bird and a plane operates differently, a plane doesn't fly like a bird does. The birds and the planes are bound by the physical reality of aerodynamics, just as our brains and computer programs are bound by the fundamental principles of information theory. So that leads us to our silly Nazi fighting genius. So if you didn't know who that was, just leave now. Okay, good. So that's of course Alan Turing. I like this looks right. Is it? It's 1L. I hope so because it's on the slide. That he invented this thing. I don't know. It was like computability theory or computation theory or something. I don't know. It's pretty niche. But the reason why I got silly there is this is a funny story, but apparently at Bletchley Park when they used to try and break the codes, like if the operators of the Enigma machine made a mistake, they'd call it a silly, which is just like the most British thing I've ever heard. It's like it's wartime, everyone's gonna die, and they're like, oh, the Germans did a silly. Let's have a cup of tea. They probably had that exact conversation. So, here we go, I needed computation theory. Right, so, you know, if you are a computer scientist, then you pray at the Church of Church. And I just found out recently that in the analysis, the large-scale analysis of the termination behavior of programs, if you draw out the Turing number for the running time, you get this interesting effect. So you can write it out as a matrix. It turns out that there's this thing called the Shroud of Turing. So here we go. First you get Jesus' face. Yeah. But you look a bit closer, that's actually Alan Turing. But then they did some more research, like this can't be right. Turns out it's just the game of life underneath. Now I blatantly stole those gifts. But it turns out if you Google Shroud of Turing, you're not disappointed. There's more stuff, it's all great. So Church-Turing. The Church-Turing thesis is that any effectively computable function, or any effectively evaluable function, can be computed by a Turing machine. So that basically means anything can be computed by a Turing machine if you accept the thesis. So at first that seems simplistic, but then you start delving into it more and you take it apart and you realize what it means is that everything, because a program can be taken apart into zeros and ones, into bits. So if everything that you can compute, so therefore everything that you can think, because our brains are computers, can be reduced to a bit string. And you go, well, but that means that you reduce like love, hate, empathy, intuition, the smell of clean laundry, the color red, all just to zeros and ones. And on the surface, that's not very fulfilling. It makes you go, oh. Like, I don't know, it seems like there's this chasm, this gap between the soft, the intuitive, the ethical, the human, and these things that encode information, that are zeros and ones. And they are just on or off, and you have a lot of them, and it seems like these things are not flexible, that they're rigid, crystalline, boring, inhuman. So, here we go. sometimes I feel like you go, well, okay, you got bits, and then some magic happens, intelligence. that's the ML bit. That's the ... And I feel like that episode of South Park where they're like, you know, they meet the underpants gnomes, and like, one, collect underpants, profit. Like, what? So what's step 2 again? Yeah, so, but if you accept the Church-Turing thesis, then everything is just bits in motion. It's just information moving around. Well, almost everything. And if you don't accept the Church-Turing thesis, then the rest is magic. So, we don't know how to do magic yet. We don't know how to do magic, so the rest is information theory, and the rest is fair game for people who want to do machine learning. So, this demo, some of you may have seen if you've been to the Python meetup, but I just thought I'd throw it in again because it's just so interesting. And I'm just going to check the time, make sure we're running over. So, the point in this model is to look at, well, what are some kind of like ways we could see the connection between zeros and ones and this flexible, more intuitive thinking and reasoning. And it's not there, but you can see the tiny shadow of it, the glimmer of it. So here we go. Here's a visualization of this thing called the restricted Boltzmann machine, which is a big mouthful for a reasonably kind of a concept that can be explained very intuitively. So each one of the squares there is a neuron, and it can be either on or off. So in this model, there are 500 neurons. So that's like, you know, 10 to the 2, and there are like maybe what, like 10 to the 11 neurons in the human brain, so like a sixth of the way there. So this black square on the right is kind of its retina, and there are connections between each neuron and the retina. And this is extremely, extremely simplified model of how something could think. It's just that we get to experiment on its brain in front of everyone, and no one has like any ethical problems with it, which is awesome because, you know, that's the other great thing about building aliens, is that we can experiment on their brains. So what you're imagining is that each one of these is the neuron of a simulated brain. And this thing here is its retina. So we're going to draw something on the retina. That's my really crummy 2, right? Now, what's interesting is that sometimes you're training a machine learning model to do something supervised, like classification, where you see something and you say what it is. This model was trained something called unsupervised, which means that it was never told what something is. It was just shown a bunch of data. And the way we constructed the algorithm was hopefully that it would find structure in that data. So if we look at some of these neurons, we can see that there are pieces of kind of digits. And it's like an identity kit of digits. Just like when you have an identity kit for a face, there's like some eyebrows and some noses and some eyes and some mouths, and you put them together and you get a full face. You can see, and that would be a good way to learn what faces are, because you'd learn the little parts and how to put them together. So in this one, we can see that there are some kind of strokes, and there are some lines, and there are some loops, and there are some kind of bits of things. So I think, try and find one here. Here we go, there's just a kind of an abstract little whoosh, which might be useful, say, putting together a 7 or something. So now we can say, resample the hidden features, which means show me what neurons are activated by this pattern, this visual input. And so, the also thing to think about this one is we introduce some randomness, which is useful, we'll see later on. But if I resample the hidden features again, you see some are just on the edge, they'll go on and off. Some are really stable and really strongly activated, and some are very strongly deactivated, they just won't go on. So you can see that, for example, this pattern here is keeping kind of this part of the picture black, so it's kind of like the missing bit of the 2, and that's a pattern that's been activated. And there's some kind of, here's a horizontal line that is kind of forming, say, the bottom of a 2. So you can see that it's taken the constituent parts of this thing and used nothing more than pattern recognition to pull it into these, to pull out these patterns, which could put it together. So what we can also do is say, well, what if, so imagine if you had a person, and there's like some movies about this, like Inception or something, where you can enter someone's dream, and you can look at what their dream is. So with this model, we could also say, well, what is it dreaming about? Like, what is it thinking? What does it see really? So what resample visual field does is it goes the other way. So one way we're going input to the neurons. We're saying what neurons turn on and off. We can also say, well, from the neurons that are on and off, what pattern would we reconstruct from that? So if we do that, then we get it's kind of like percept, or at least a visualization of its percept of a two. So what is interesting about this model is that we can now go back and forth, and there's a little bit of randomness involved, right? So if I do go back and forth, then what's going to happen is that we'll kind of go between things which are similar but different. They're unmistakably twos, but, you know, for example, the top is a bit more curly, the bottom is a bit longer or shorter, and sometimes if we run it long enough, we'll see it go into even a different style of two. So what we see here is like the very, very smallest and simplest seed of analogy, where we can see that, oh, hang on a minute, like this pattern is similar to this other pattern. And everything that's going through here is, yeah, it's just parameters, like they're just floating point numbers. If you're a practitioner, we just fit them with a reasonably simple algorithm that chooses, you know, how we should tweak our floating point numbers. You know, should some go up, some go down to fit the data better or worse? So what are the other things that we think intelligent objects, are people objects? It's kind of a bit reductive. Intelligent things? People are the things either. Intelligences, I like it, I just avoid it altogether. So intelligences. What other things do intelligences do? One of them is be surprised. That sounds like a pretty useless skill, but actually it's pretty good. Like one of the things that separates us from kind of like a bacteria is it can be genuinely surprised when like, people still like Justin Bieber. Like, what? How did that happen? So if I do something that is manifestly not a digit, and then we run it, what's going to happen is that it's saying there's very few patterns there. Very few neurons really stimulated, and also its reconstruction of that input is incredibly poor. So what we're seeing there is it's being like, hey, that made no sense to me. Like that's not a pattern that I'm used to. That's not a pattern that I've seen. I'm surprised. It's kind of like, you know, detecting an anomaly, or that is finding something out of pattern. And I think that that's again one of these things which we see as, yes, intelligences have that, but how do we get them from just numbers, from just zeros and ones? And one way to do that is just through, again, pattern recognition, like these kind of like overlaid, stacked pattern recognizers. So now, the other thing that humans are really, really good at, and computers seem mostly bad at, although they're getting better because of some of the algorithms that are similar to this, is telling us between the signal and the noise. So we can tell, for example, what people are saying even though we're in a noisy bar. We can read messy handwriting, and those are all things which for the longest time very, very, very hard for us to program computers to do. So if I, for example, say, well, hey, here's a 3, but I add noise. So I'm saying, hey, this is a corrupted 3. And I'm saying, hey, now I'm going to run you. I'm going to resample my hidden features, and I'm going to see what neurons are activated by this pattern. And then I say, well, what did you see? What is the thing you actually clearly saw? And if I resample the visual field, you say, we still saw the 3. We saw the 3 without noise. We saw the concept of the 3 as embodied by those neurons that were activated. And so the last property that is easy to demonstrate with this model, which is why I'm mentioning it now, is inference. So things that are intelligent tend to be able to figure out what the unseen whole is from an individual part. So we can kind of see a person hiding behind a bush and be like, why are you hiding behind a bush? Are you drunk? There's like one person that found that funny. So what we can do is we can say, well, okay, we're going to draw something which is like part of a digit. This is kind of like Mr. Squiggle, you know. And then we're going to lock it, and we'll say, well, okay, don't let those change. It's like burned into your retina almost. Or, you know, it's a model. We can do what we want to it. And then we're going to run it. And what we're going to see is that as we run it. So one of the last things we can do, and I think this is funny, is we can also say, well, the last thing that intelligences seem to do for our sample size of 1 is dream, sometimes. And we can say, well, okay, just dream. Like, here's nothing. Here's a blank canvas. Just what happens? So if we run it, we can see that some neurons randomly come on, and there's some kind of random activation, and it's kind of moving around, nothing's happening. And then you might see a seed from something, like the seed of an idea, so they can keep growing and keep feeding back and activating these neurons, which match part of the pattern, so that those neurons then fill it out. And you can see now it's sort of starting to do inference on this seed, saying, well, hey, what could this seed form? And then, as it continues to think and continues to dream, you can see, oh, it's dreaming in kind of like in blobs and shapes. Then you're, okay, well, what is it? Let's keep going. Oh, hey, it's 9. There you go. So it's a dream. It's like dreaming about a 9. It's pretty boring, but I guess if all you've ever seen is 9 digits, you're going to dream about 9s. So I think that you know, using the term dreaming there is a bit overloaded. You're actually just randomly flipping these bits and then seeing what happens. But the fact that when you randomly flip these bits, and if those bits are chosen correctly, you get something which is almost tantalizingly close to being kind of smart, is what really excites me. And the fact that even with only 500 neurons, you're getting something which is almost kind of doing something useful, thinking in a useful way. Like if you squint. So, oh yeah, I promise you'd find it. So there we go. You just fell in love with 300,000 floating point numbers as a character. So perhaps not fell in love with it. But I wrote a little message that said, "Do you love me?" But it was just noise. It was an anomaly. So the other thing that we can do is create a really badass dictionary. So this is a project from Google, Word2Vec, look it up. It's amazing if you're into NLP, that's natural language processing in any way. Like, if you haven't already heard about Word2Vec, like run, like just leave now and go download it. Just don't listen to the rest of my talk. And then what they did was basically they created a dictionary for all the words. But the difference between this dictionary and the ones that people use is that each word, instead of having the letters that make up that word, was just like 300 numbers, so it was just a vector. So, and hence the eponymous Word2Vec is saying, hey, here's a dictionary, you take a word and it gives you a vector. And that may seem kind of stupid, because you're like, well, yeah, I had a word and I understood what it meant, and they've given me 300 numbers. What are 300 numbers good for? Well, it turns out that if you, that these numbers, so the way we've chosen them, and the way we've chosen them is by basically, we built a neural network which takes as input these numbers and tries to predict the words around that input number. So like, you know, for example, if your word was like, you know, king, it might be King William said, and it would have to predict from your input, King William said. And the reason why, so then we'd optimize it so that the vector that corresponds to these words was useful for solving this task. But it turns out that if a vector contains enough information to solve these tasks, it embodies something about the meaning of words. And so one way to think of it is that we've embedded these words in a semantic space. So normally the words in letter space aren't semantic. If you look at the letters of a word, it has very little to do with its meaning. A little bit because of those phonetic connotations, but very, very little. Whereas this particular representation is in a space which is semantic, so that the dimensions of the space mean something. And so here we go. The classic thing, and this was like, when the researchers discovered this, seriously, they must have had some sort of wild party. This happened to me. I would like blackout drink for a week. So basically they discovered that the difference, like the vector pointing from, say, like queen to king was the same, or approximately the same, as the vector pointing from like woman to man. And so because this is a Euclidean space, which means we really know a lot about it, like that's all your, you know, freaking linear algebra, we can just move king onto the left-hand side. So we want to be like, well, man is to woman as king is to what? We can just say, well, okay, take the vector for woman, subtract man, add king, and then see what we get. And so and it works. That's like, yeah, that's why it's funny, right? So here goes. Here's the, can I change tabs now, please? Here we go. Here we go. Is that, can people see that or make it larger? Okay, can we see at the back? Can we see? Yeah, okay. So here we go. This is a thing called GenSim. If you're into Python, download it. It's amazing. This is a pre-trained model built by Google. You can just download it. It's like a couple gig. And what this is saying is, okay, we're going to create this function called analogy, which takes A, B, and C, and it's going to add B and C. So that's saying like, okay, take our, I don't know, I have to get my head on straight about this, but it's like, here we go. We're going to take woman, we're going to subtract man, and we'll take queen and subtract man, and then we're going to add woman. And hopefully what we get is queen. So here's what we're doing here. We can say, okay, here we go. We're going to say like, woman is to man. Oh, sorry. Man is to woman. Is to woman as queen is to prince. Oh, yeah. Man is to woman as, oh, king. Yeah, sorry. That was the wrong way around. Here we go. King to queen. And then if we put it around the other way, woman is to man, right? As, yeah, queen is to, and then we get king, yeah. So that's cute, right? And the thing that I had primed it with was we can even do like kind of like fairly, so we can do some syntactic concepts. So we can say like small is to smallest as big is to. And then we get biggest, and so there's syntactic regularities, which is exciting. But yeah, syntax and then kind of like common facts is like, yeah, that's great. But let's do a capital just to convince you it works. So we can say like, for example, Japan is to Tokyo as, for example, France is to. Hey, Paris! Wow, it works. Yo, 10.
So how far can it go? Can you do like hairy is to bald as rough is to smooth?
That like fine.
Tell me.
Maybe.
Right.
This is what we're all about. So hairy is to bald as, is this like? Okay,
yeah, because they're related obviously, but like they're syntactically
rougher. Yeah, not really. It does a pretty shitty job of that one. One thing is you can do like, yeah. Yes, let's try that. Good is to bad as life is to lives. Yeah, you're getting something syntactic there. So, interestingly enough, that is really screwed up. There are some really funny ones. So let's actually try capital L life as in the, no, that's awful. So, so if you do white is, so one thing that I found is that some things it tends to do really well. I think maybe that's like, that's an interesting philosophical question. Maybe, yeah. So if we do dark, this is one that I was really surprised by. So light to day is dark to night. Which was like, yeah, that was like, hey, that's pretty close. Yeah. But what really interests me though, and this is, it's cute, but whatever, we could do that with the database, who gives a shit. But one thing that it did learn, this is when I started getting really excited, when I started trying it on things which are really cultural. So you can be like, okay, Apple is to iPhone as, oh yeah, here we go, Google is to, and then we go Gmail, search engine, we do Microsoft, and then you get Windows Mobile, and so, but then you can ask kind of like more abstract things. You're like, okay, so this is what really excited me. Like, singing is to Ella Fitzgerald as trumpet is to, and then go, hey, Dizzy Gillespie. And I'm like, damn, that's fucking awesome. And so this was trained unsupervised. And so the thing that I really like about this is it's getting cultural stuff, not semantic stuff. No, it's not always symmetrical. it may not, simply because what we do is we search for a nearest neighbor. So sometimes you don't get the correct inversion. But yeah, here we go. Dizzy Gillespie, Ella Fitzgerald, and it's trumpet. Yeah, here we go. Harp. It gets that it's a yeah. No, well, it gets that it's a instrument, but yeah. So again, this is using vectors of like 300 numbers, which is not a lot of zeros and ones. And so going back to our information theory thing, we say, well, okay, how much information is there really in that? But what's this showing? What this is showing is if you choose the right information, so you choose the right zeros and ones for your vector representation of words, you get a lot of structure out of those zeros and ones. Zeros and ones can have a lot of structure, which is starting to just grasp at meaning. And yeah, like a lot of the examples that we tried, which were, this is the great thing about demos, is that they don't work as well when people come up with examples. That's why we do them. But like you can see that, for example, with this one, it's definitely not the right answer. It kind of is maybe like a category, like there's something there. It's really trying hard to give us something that makes sense, but just badly failing. But yeah, it's 300 numbers. And yeah, there is a real question: what happens? How many neurons in our brain do we use to represent one word? And it would be order of millions to billions. And so, if each one of those neurons was corresponding to like a handful of floating point numbers in a very, very rough approximation, then maybe if we were coming up with quality semantic spaces of say 1 million dimensions, we could get something which is a little bit more kind of like useful for separate kind of querying. So another one that I wish I had my notes open. I just you know what? There are some funny ones. But I'll keep moving. But let's see if I can remember one. I'll try. Here we go. Girl is to, I think it was Barbie. Yeah, as boy is to. Let's see if Hot Wheels. Yeah, yeah. There you go. Yeah, okay, here's a funny one. This is a surprisingly good answer. So we go, pop is to, and sometimes is that how you do it? As classical. I was like, who was the Justin Bieber of classical music? Oh, Justin. Thank you. And so, how is it spelled? B-E-B-I-E-B-I? Okay, good. See, I'm. I think maybe one of them needs to be capitalized. Oh yeah, classic. So the answer we came up with was Lamb Lamb, which I'm pretty surprised about. Nah. Classical music, maybe? I think that's praise. Oh yeah, hey, Lang Lang, there you go. Which is kind of true, he's a bit dramatic. And then you get your Mozart in the list, which doesn't make sense. So yeah, there you go. Mozart is a Justin Bieber of classical music. Hang on a minute. We can do Ella Fitzgerald as well. There we go. Jazz is to Ella. I promise we'll stop playing this now. Jazz is to Ella Fitzgerald as pop is to. There we go. Hey, Mariah Carey and Whitney Houston. You're like, yeah, that is a culturally apt response. Like, and that's what I like. It's something that it's very hard to capture with like a rule system or a database, and that's what these squishy things are good for. Like the
Can we change like to an obscure jazz person instead of an obscure pop artist?
Yeah, let's try it. Yeah, so yeah, it's like, come up with an obscure jazz artist on the spot. Yeah. There's people judging you now. Like, hey, is this guy really a hardcore jazz fan? How is it? No, Miles Davis is Infamous Month. Art Pepper. Anyone have Art Pepper? Yeah, that's right. Yeah, we'll find out. Art Pepper is not in the database. See, he's that obscure. I know.
It should have returned something else that's not in the database.
What's that? Oh yeah. So yeah, it should have given us something else that's not in the database. So yeah, indeed. Here we go. So this is the little bit technical part of the talk. So when we're building models, with this, if you accept the Church-Turing thesis, then everything is at least representable as a bit string. So that turns our job into finding these bit strings. And I think a really important property that models of the future are going to have, and I believe that large recurrent networks do, is this property that I've been calling Turing consistency. The idea of Turing consistency is that most machine learning models, as you can increase the number of parameters they have without bound, don't cover the space of all possible computable functions, in the sense that they don't learn anything that could be learned, that there is only, they have a way of looking at the world which they have, and that if it doesn't fit with that, then they'll never learn to solve that problem. Whereas something Turing consistency means that as you make it big enough, it will learn anything that can be learned. And that's a pretty useful property, that's a strong property. And in many ways, as we look at the development of kind of like deep learning today, we see that not that much changed. Most of it was just the availability of more computing power. And I believe that is a big part just Turing consistency. That if you have a Turing consistent model, which is provably Turing consistent, then at some point you can just add more computational power and it will do better. You need to add more data as well to fit the model capacity, but basically more computation, more data for a Turing consistent model, it will get better. And that's not true for most models, and is for very large neural networks, recurrent neural networks. So yeah, enough parameters compute any computable function and learn anything that can be learned, which is like, that's a pretty strong statement, but you know, if you can learn any computable function and computable functions are all there is, then, oh hey, Bob's your uncle. Easy, problem solved, you can all go home now. And then the other property I think is like really important is this property I've been calling Bayesian stability. And I'm not so happy with the name of this one, but I needed something to put on the slide. So basically, a model will be surprised by stuff. Like stuff will happen and it will be surprised. Like when you first pointed at those two flashing lights that flash together, it will be equally surprised by one light on, one light off, as it will be both lights on. But as it learns more about it, as it learns to represent this system, which is incredibly simple, it will be very unsurprised by both lights on, both lights off, just as we're very unsurprised by most things that happen in our life that, you know, like when we touch something and we feel it, we're like, oh, that's not surprising. When the sun rises, we're like, I'm not surprised by that. That's because we've learned. And so Bayesian stability, I think you would come up with some like reasonably good rigorous definitions, but the heuristic definition is more data, less surprise. And so that means that your model surprisal in the limit as you get enough. So we're all really doing program search in the end. It's a very, very abstract notion of what we all do, but in the end it is. And when you reduce it to its core elements. So here we go. Some bit strings are intelligent, some are not. Yeah, and we basically define which ones are, we find them. We're intrepid explorers exploring the space of programs. So here we go. This is a classic quote. If you haven't heard it before, well, hey, here it is. The question of whether machines can think is about as relevant as the question of whether submarines can swim. So, submarines were never meant to swim like fish, planes were never meant to fly like a bird, dry brains aren't meant to think like wet brains. But there is something in common, and that is that birds and planes are both bound by aerodynamics, dry brains and wet brains are both bound by information theory, and that is the fundamental theory that governs both of them. So, that's your takeaway. Here we go. I'm Andy Kitchen. I will meet you all. Thank you for coming. Yeah, let's see what let's do. Let's see if we have time for questions. Oh yeah, hey, we've got that was good timing on my part. Wow. I'm surprised that talk managed to fill up so much time. If I spent 4 hours starting and then we're talking for an hour, it's a pretty good yield. Yeah, yo, Gerald.
First question was,
yes,
so
anything.
About word to vec, right?
Yeah.
Reduces a word to a 300-member vector space.
That's right.
How do they, I guess, assign the numbers? Like what's the parameter? Like, you can sort of imagine that in your one, your restricted Boltzmann machine is kind of like a picture to vec. When you have a picture and you reduce it to a vector, however many neurons are being activated.
That's a brilliant insight. You're a smart guy, Gerald. That's why I like you.
But you've got pixels, right? So
yes.
A discernible bit of on and off.
Yeah.
But in a word, you don't really
Yeah. So
Can we get the question repeated?
yeah. So Gerald's question was, how the hell do we find good vectors to represent words? It seems like pretty magic, like magic. Yeah, really, right? So the answer is that we have a dictionary. So we would just probably initialize that randomly, but every word has a vector. Then what we do is we build a neural network, which we're eventually going to throw away, but we build it. And that neural network will get as input the thing in the dictionary. So we'll see a word, like in this case, king. And then the neural network will get king as input. And then from king, it has to predict the words around king. So the words around king could be like King William, King Regent, I'm the king of dance, which I have said probably once in a club when I was drunk. And so what happens is then we back propagate that all. So we take the gradients, and then if the word representation in the dictionary we could have tweaked to make the answer better, then we'll do that. So if for each example, like each word it's shown, we'll say, well, hang on a minute, if that dictionary had been a little bit, just say, and this is not probably how it will work, but just say there's one dimension, which is whether something is masculine or feminine, or considering it's such an important concept, there might be. So there's at least some linear subspace. Let's say it's rotated so that linear subspace is axis aligned. Then there will be a dimension which is masculinity or femininity. And then we'll say, hang on a minute, this king thing, you would make a better prediction about this word if it was more masculine. So we'll just bump up the masculinity a little bit. And we'll do that millions and millions of times over. And eventually we'll massage our word vectors into being good at good representations for this neural network to use to predict the other words. But what's interesting is then we just throw that neural network away because it's not important. But those vectors which were good for predicting the next words are also good for doing other things. They have these kind of interesting properties. And so the answer is we found those vectors by finding good vectors as input to predict other words. So in the case of the images, each image is only shown one at a time, but with the words, we show words together with their context. And that's where it gets its information from. Because each word, it doesn't actually even get to see inside the word. Like we could replace the words with numbers or gobbledygook, and it would still come up with the same vectors. Any other questions? We have probably time for like one or two more. Huh? Oh yeah, hey, there we go. That one.
Will you be storing this whatever it is, PowerPoint, onto the website somewhere so that I jog our memory to remind us?
And with references, so that you can read the papers behind all the crap that I rambled about and understand it actually properly. Dan?
Yeah, so it's just like a bit of a dear lazy web question. A lot of these examples are around, there's just some like data set and you kind of learn to sort of search within it. But not a lot where like there's some difference between like objective facts versus subjective facts or trustability. Whereas like in human science, the concept of objectivity and measurement is central to belief, valid belief, whereas that doesn't seem to get into these systems very much. Does anyone know of anything that tries to do that?
Right. Well, I think that fundamentally there are kind of a few different ways to build models, and practitioners will be very intimately acquainted with them, but I'll just go through them really quickly. So the question was, how can we know what data is good and what data is bad, and what decisions kind of we should make about the world? I think that was the kind of paraphrasing. But how do we know what good?
Just that little bit extra to we know that objective measurement of the world is very important for like science, and so like weather forecasting goes back to like physical modeling above statistical learning. So the physicality, like the explainability, the fact we can take it back to a measurement of a temperature sensor of the world, which is beyond us, which is beyond just our sensory bias, taking it to this concept that there's this external transcendental world and we need to measure it to be right. And that is fundamentally different from what we think, believe, perceive, and feel.
So I think that let's just say that there are these ways to learn different things. One of them is so this will get there, but I just have to lay a bit of groundwork for people who aren't like intimately acquainted with how machine learning works. So there are these things called supervised models, and a supervised model means you tell it the right answer. Like, this is a picture of a cat, this is a picture of a dog, this is a 3, this is a 9. And supervised models just trust whatever the fuck you say, and that's just the way it is because you're God. You built them. Then there are unsupervised models where you just give them data and you say, hey, there are some patterns in this data, go find it, but hey, whatever, man. And then there's also reinforcement learning. And reinforcement learning is where we get some kind of reward for doing something in some world state. So we're going through the world, happy, blah-de-blah-de-blah, and then, we decide that we're going to do a backflip, and then some guy's like, hey, that was cool, and we get some reward, and then we want to do backflips more. So that's a terrible example, but the point in that is that you don't know, but you could have spent like 3 weeks learning to backflip. You don't know necessarily when that reward will come or what will trigger it. And in fact, if you get a reward, you might have some guy might 3 weeks later be like, hey, by the way, I saw you do some unspecified thing and it was cool. And you'd be like, was that because I backflipped that one time? So that's the trouble of like reinforcement learning. And I think that reinforcement learning, while not being perfect, is a pretty good model for how humans actually go about the world. And in that case, maybe there is some sort of like objective transcendental reality, but either way, like the reason why we take stock in it is just because like if we make good predictions about the world from like thermometers and computer screens, we don't die more, and we like that. So I think you can kind of sidestep that a bit by saying, well, if your reinforcement structure is correct, which is ours is pretty strong, it's like don't die, survive. Then if your reinforcement structure is correct, you'll start believing anything that will help you to survive. And I think that that's what you notice about people in general, is that they don't believe necessarily the objective world. They believe what helps them get by. And for some people, that's like science and technology because they're fucking nerd geeks. And for other people, that's like their religion and stuff. And I think that it's interesting that if you analyze, say, that way of thinking in a very kind of dry information theoretic model, like one that doesn't put a lot of onus on like humanity particularly, it's like what is intelligence outside of people, then it's like whatever your reinforcement structure is, you're going to try and kind of optimize that, and that's survival. So you're going to try and survive. That's what you do. Yeah. So to answer your question, I think these things don't really know what is the objective world and what isn't. We've just given it to them. Yeah. Okay. One last question, and then I think we will go and drink. Or
not a question.
Yes.
I thought I'd throw into the mix that Alan Turing in his 1950 patent, I think it's called Computational Machines and Intelligence, he basically said that AI would become by learning like children.
Yeah, that guy was smart. Probably a computer. What's that? Oh yeah, time traveling computer. Built from nano machines. Yeah, built by future humans too, so that we can built by future AIs, sent back in time so that we can invent AI. Alan Turing, everyone. Thank you all for coming. I think we're going to go upstairs. Thank you.